Let's start by getting our brains moving and thinking about what we already know about how to identify different kinds of functions. So this is a copy of some work that's in your book, and it asks you to match each equation with its graph. But there's no equation really listed. All there is a description. So it says, problem 3, I'm looking for a linear function, 4, an exponential function, and 5, a quadratic function. And then there's 3 graphs down below. Well, here's what I notice. I can tell right away that graph B represents a linear function, because if I look at the points in graph B and connect them, they all form a straight line. I can tell that graph C represents an exponential function. If I were to connect the points in graph C, they would represent exponential growth. And I can tell that graph A is a quadratic function. Those points, if I were to connect them in a smooth-ish kind of way, would form a parabola. And I know that a parabola is the graph of a quadratic function. So you can tell by looking at the picture of a graph what type of function it is you're dealing with. What we need to do in this section is learn how to identify from a table what kind of a function we're looking for, and more specifically, to be able to create an equation for a function given some points on that function. So first, let's review what we learned about linear functions in the first half of the year. Linear functions form lines. That's why we call them linear functions. So I'll show you some pictures of linear functions. Here's one. This one has a positive slope and a positive y-intercept. Here's another one, positive y-intercept, but this one has a negative slope. Here's another one that has a slope of 0 and a negative y-intercept, and we could go on for a while. The general form for a linear function was y equals mx plus b. M is the slope and b is the y-intercept. It's key in this case that there are no exponents anywhere. Our variables are x and y, a plain old x and a plain old y. If we had a table of values, some x's that I put in and some y's that I got out, I could tell that this table represents a linear function by comparing how y changes with how x changes. So as x gets increased by 1, so x is going up by 1 every step, y is going up, we're adding 2 to y. We're adding a constant amount to y every time. If I wanted to figure out what's my rule for the points in this table, I could identify that m is the slope, which is the rise over run. I can tell the rise from looking at the bottom half of this table. It's positive 2 because y is going up by 2. And the run from looking up towards the top of this table is positive 1 because x is going up by 1. So rise over run would be 2 over 1. That's what m would be. To find the b, the y-intercept, I can look for the point in the table where x is 0 and y is some number. That some number that y is, that's our b. So in this case, the equation of the line going through all the points listed in this table would be y equals 2x plus negative 1. Next, we learned about exponential functions, and we did these in Chapter 8. We learned about exponential growth and exponential decay. The key thing about exponential functions was that the variable was the exponent. The general form of them was y equals a times b to the x power. Notice the variable is up in the exponent there. And they generally were either exponential growth or exponential decay. If we had a table of values, we would compare how x changes and how y changes. So in the table shown below, x is being added by 1 every step, but y is being multiplied by 3. This idea that the ratio of 2 consecutive y terms, the word successive means they're next to each other. Consecutive means they're next to each other. So if we compare 2 y terms that are next to each other in this table, each time we move a step to the right in the table, we're multiplying by 3. So we could find the general form of the exponential function shown in this table. We could identify what a and b are by looking at the table. A is 0, 1. It's what I get out when I put in a 0 for x. So in this case, a is 1. b is just the number that I'm multiplying by every time x is increased by 1. So the equation that matches the function shown in this table would be y equals 1 times 3 to the x power. Now we're working with quadratic functions. When we graph quadratic functions, they form parabolas that either have maximum values or minimum values. They have the general form y equals ax squared plus bx plus c. We've learned that a changes how the parabola opens, c is the y-intercept of the parabola, and b shifts the parabola left and right, up and down. One variable is squared in one term, and you may also have a variable that has an exponent of 1 on it. In this case, that's the middle term, b times x to the first power. Here's a table of values that goes with a quadratic function. How could I tell from looking at this table of values that these represent a quadratic function? Well, I need to do 2 steps. I notice that in this case, x increases by 1 as we move a step to the right in the table. And I have to look twice at y. This phrase second difference that shows up here, difference means we have to do some subtracting. Second difference means we have to do some subtracting twice. So to get from 8 to 2, I'm going down by 6. To get from 2 to 0, I'm going down by 2. To get from 0 to 2, I'm going up by 2. And to get from 2 to 8, I'm going up by 6. Now I have this pattern of numbers beneath my table, -6, -2, +2, +6. I'm going to repeat the same process on this new sequence of numbers. To get from -6 to -2, I'm going up by 4. To get from -2 to +2, I'm going up by 4. To get from +2 to +6, I'm going up by 4. We call this the second difference. The first row under my table is the first difference, and the second row under the table is the second difference. The second difference in this case is constant. It's 4. This tells us that this is a quadratic function. In Algebra 1, we're only going to be working to find the a for simple quadratic functions that have the general form y equals ax squared. Later on, you'll figure out how to find out what b and c are given a table of values for a quadratic function. So how do we find out for the table shown above what a is? Well, we're going to pick a point from the table where neither x nor y is 0. I need non-zero numbers for x and y. Doesn't really matter which point I pick. I'm going to pick the point 1, 2. That's one point in the table where neither x nor y is 0. And I'm going to plug x in, 1 in for x and 2 in for y in the general y equals ax squared form. When I do that, I see that I have this equation, 2 equals a times 1 squared. This is an equation that I can solve for a. When I do that, when I get a all by itself in this case, I get that a equals 2. So the equation that goes with the table shown above is y equals 2x squared.